Hi, this lesson is about the fundamental theorem of calculus, part 1. So remember, the fundamental theorem of calculus, which I'm abbreviating as FTC, that provides the inverse relationship between the derivative and the integral, the two main parts of calculus. So we talked about part 2 in a previous lesson. Now we're going to talk about part 1. Part 1 is here in this green box. So if f is continuous on a closed interval from a to b, then the function g defined by g of x equal to the integral from a to x of f of t dt, where x is between a and b, is continuous on AB. So in other words, g of x, which is an integral, it's g of x is being defined as a function, is continuous on AB and also differentiable on the open interval from a to b. And if that relationship exists, then this must be true, that g prime of x is f of x. Because remember, derivatives and integrals are inverse relationships. So if you're taking the derivative of an integral, as we would be in this case, the derivative of g prime is just your function in terms of x. Okay, so let's use this theorem in a couple of different ways in these examples. So given the following graph of f of t, and given that g of x is equal to the integral from 0 to x of f of t dt, we want to evaluate g of 0, g of 1, and g of 2. So remember, an integral represents an area. So we're going to use that information in order to calculate g of 0, g of 1, and g of 2. So here's our graph. We can see that f of t is continuous from 0 to 4, so it satisfies the initial condition here for fundamental theorem of calculus part 1. G of x will represent the area under the curve of f of t, because g of x is the integral of f of t. Well, g of 0, when you're at 0, well, you don't have any area there. Remember, when your limits, beginning and ending limits, are equal, that means there is no area under the curve, and therefore the integral has a value of 0. We also talked about this in a previous section when we talked about properties of integrals. Now let's move on to g of 1. G of 1 is here. So if you look at the area under the curve from 0 to 1, and the reason why it's 1, because remember, x is 1, that's just a triangle. So we need to use the formula for the area of a triangle, which is 1/2 base times height. That's what you see here. So the base is 1 unit, the height is 3, so g of 1 has a value of 3/2. Now let's move on to g of 2. G of 2 from 0 to 2 is the area of a triangle and a rectangle. So we can add those two areas together to evaluate g of 2. And that's exactly what I wrote here, that the integral from 0 to 2 of f of t dt is equal to the integral from 0 to 1 of f of t dt, and the integral from 1 to 2 of f of t dt. Well, we did this integral in the previous example. We know that has a value of 3/2, so I just wrote that down. And to compute the integral from 1 to 2 of f of t dt, well, that's just length times width, because it's a rectangle, as you can see from the graph, where the length is 3 and the width is 1. So when you add 3/2 and 3, you get a result of 9/2 for your area. Okay, so we're going to do a similar example here. We want to evaluate g of 1, g of 2, g of 3, and g of 4 for g of x equal to the integral from 0 to x of f of t dt. And f of t is drawn here on the left. So g of 1. G of 1 is the area from 0 to 1. This is, again, a triangle. And remember, triangle is the formula for the area is 1/2 base times height, which is what you see here. 1/2, the base is 1, the height is again 3, so I have an area of 3/2. Now let's look at g of 2. G of 2 is the entire triangle, so we can do that just in one calculation rather than splitting it up. My height is still 3, but this time my base is 2. So 1/2 base times height gives me a result of 3. Okay, you can also use symmetry to compute that. You can see that this triangle, if you split it in half, it's the same on the left and on the right. So therefore also, this is also equal to 3/2 or 1.5 plus 3/2. So it could have been done that way as well. All right, so now we have to compute g of 3. Now g of 3 means that I want to compute the area from 0 to 3. So that means I have a triangle above or to the left that I already computed. And then I have one from 2 to 3 that's below the x-axis. Remember, the placement of where your area is matters. When it's above the x-axis, your area is positive. When it is below the x-axis, your area is negative. And the sum of both will be your net area. So g of 3 is the integral from 0 to 2, because we already know that one, and then from 2 to 3 of f of t. So the integral from 0 to 2, well, that's 3. We computed that in the previous step. And from 2 to 3, we have to use our formula for a triangle. And remember, make it negative. So it's negative 1/2 times your base, which is 1, and your height, which is 3. So we have to compute 3 minus 3/2, get a common denominator, and here my area is again 3/2. Now we have to compute g of 4. G of 4, probably it's easiest to look at this in terms of two integrals. The integral from 0 to 2 of f of t dt plus the integral from 2 to 4 of f of t dt. So it's in fact the sum of the areas of two triangles. So 0 to 2, well, we know that's 3. We did that one previously. And to compute the integral from 2 to 4, again, that entire second triangle is below the x-axis, so it is negative. So we force the negative right in here. So it's 1/2 base, which is 2 units, times height, which is 3. So that has a value of negative 3. So your net area from 0 to 4 is just 0, because the area above the x-axis and below the x-axis are the same, except one is positive and one is negative. Okay, so now we're going to use the other part of the fundamental theorem of calculus, part 1, which says that if g of x is equal to this integral, then g prime of x equals f of x. All right, so here are a few examples. We want to find g prime of x for the given functions. So I have g of x is equal to the integral from 1 to x of the square root of 1 plus 2t squared dt. Now here, you're not taking an antiderivative. We're not integrating. We are finding a derivative of an integral. So g prime of x is just the integrand with the t replaced with x. So let's do another example. I want to find the derivative of g, where g of x equals the integral from 0 to x of cosine 3t squared dt. So g prime is just the original integrand, just with the t replaced with the value of x. Okay, so we get cosine 3x squared. Okay, let's go on to the next example. Here I have g of x is equal to the integral from x to 2 of 5 over t squared dt. Notice that your limits are in a different order than the previous two and different than the way the theorem gave it to you. The constant doesn't really matter. As long as the constant is in the domain, it's fine. So here I had a constant of 1, here I had a constant of 0, here my constant is 2. But the 2 is an upper limit instead of a lower limit. So we need to remember something from our integral properties, which says that if you flip the limits, that's just the opposite sign of the integral. So that's what I did here. Then I can do exactly what I did in the previous two examples. The derivative of g is just the negative of 5 over x squared. So just replace your variable with x. Okay, but sometimes these problems are not as easy as the three we just did. In some cases, your limit is a value other than x. It could be a function that's a little bit more complex than x. And when that occurs, then we have to actually use chain rule when we take the derivative of the integral. All right, so let's see how that works. Here, your g of x is the integral from 1 to 3x squared of t squared dt. Now, let's let u equal 3x squared, because that's the first time we're seeing something other than just x. So if I rewrite this in terms of u, I have the integral from 1 to u of t squared dt. So now I have to take the derivative in order to find, what we were asked to do, find g prime. All right, so if this is g of u, then when I take the derivative, this is g prime of u. And so now I'm taking the derivative with respect to u of my expression. But remember, u is something more complex than just x. So when I take the derivative, I take the derivative of think of this as like your outer function times the derivative of the inner function, which is this one. We have to take the derivative of whatever u is equal to. So I'm going to do that. So g prime of u is equal to just u squared. So this part is easy. We just replace the t with u times the derivative of du dx. But what is du dx? Du dx is 6x. So in this next line, I'm going to replace everything back in terms of x. So du dx is 6x. So here I have that g prime of x is 3x squared squared. In other words, the u gets replaced and du dx is 6x. Then the rest of it is just a little bit of algebra. When you square 3x squared squared, you get 9x to the fourth times 6x. And when you multiply 9x to the fourth and 6x, you get 54x to the fifth. Okay, so here's another example. We have g of x is equal to the integral from 2 to sine of x cosine of t dt. Again, I have something other than just x. My limit is a function. So first you take the derivative of the integral, which is just the cosine of sine of x. Replace the t with whatever's in the limit, times the derivative of the limit, the function that's in the limit, the derivative of sine of x. Well, the derivative of sine of x is cosine x, so your answer is g prime of x equals cosine of sine of x times cosine of x. And you cannot combine those cosines, their inputs are different. All right, so to expand upon this, this is a slight variation to the theorem that I gave you before. But if you have g of x equal to the integral of f of t dt, where your limits are two functions, and I'm going to call the lower limit u of x and the upper limit v of x. So suppose they're both functions, not constants at all, and not just a single variable of like x. Then when you take the derivative of g, that's going to be f evaluated at v of x times v prime minus f evaluated at u of x multiplied by u prime. So this might remind you a little bit of the fundamental theorem of calculus part 2, where you're inputting your upper and lower limit, right here, inputting the upper and lower limit into your antiderivative. But remember, we're not integrating, we are taking a derivative. But there is a relationship here. So let's use this to compute this example. So I want to find g prime of x for g of x equal to the integral of 2t dt from sine of x to cosine of x. So again, we're just following this rule right here. So that's going to be 2 cosine of x, because first you input the upper limit, times the derivative of the upper limit. What's the derivative of cosine? Negative sine. then it's minus, right? Okay, we're using that formula, minus, and then it's your function, 2t, evaluated at your lower limit. And what's my lower limit? Sine. So that's what you see here, times the derivative of sine, which is cosine. So then the rest is just a little bit of simplification. So you get negative 2 cosine of x sine of x minus 2 sine of x cosine of x. Well, those two are like terms. So your g prime of x is negative 4 cosine of x sine of x. Okay, so let's do another example where we're using the theorem that's in this blue box where I have limits that are both functions. So I have g of x is equal to the integral of square root of t dt, and I want to find g prime where your limits are 2x to 4x. All right, so first step is input the upper limit into the radical. So that's where we get square root of 4x times the derivative of 4x, which is 4, minus input the lower limit. So I get the square root of 2x times the derivative of 2x, which is 2. Then the rest of it is a little bit of simplification. So this is equal to 4 square root 4x minus 2 square root 2x. I just put the coefficients in front. But the first radical simplifies. The square root of 4 is 2. And when that comes out of the radical, it gets multiplied by that 4. So we get 8 square root x minus 2 square root 2x. So that's it for this lesson. You're ready to try the homework. Good luck.